Okay, so good morning everyone. So in today's lecture I am going to talk about the final topic regarding the final topic on the necessary condition for finding the extremal of the functional, namely on how to find the transformation or the variational symmetry that leads to the conservation law. Remember, in my previous lecture we had spoken about Noether's theorem, which relates the variational symmetries with the conservation law. So all it remains now is how to find these variational symmetries. So then towards the later half of this discussion, I am also going to touch upon the new topic of finding the sufficient condition for an extremal, namely the topic on second variation. So the topic will cover today two parts. First we will cover we will discuss about how to find the transformation or the variational symmetries that lead to the conservation laws. Okay. And the second half of this discussion will involve finding the second variation and second variation of the functional. Okay. What is the use and why do we need to see the second variation? Okay. So as I had mentioned in my previous lecture, Noether's theorem provides me the conservation law, if we know the variational symmetry, right. So the key is to find these variational symmetries. Let me denote it by Vs, right. So which means, or in other words, all we need to find are the infinitesimal generators of these transformations. Okay. So only thing that we need to find, infinitesimal generators zeta comma eta that we saw in our previous lecture. Okay. So without going much into further discussion, I am going to right away provide the results on how to find these infinitesimal generators, and the result is in the form of a theorem. We will use this theorem in some of our examples which will follow next to look at how to apply this result. Okay. So let us say that we are given a functional of the form integral x naught to x 1 f of x comma y prime dx, the transformation, and we are given the transformations x is equal to theta of x y epsilon and y is equal to psi of x y epsilon. So these are my my transformations with infinitesimal generators, xi comma eta, infinitesimal generator xi comma eta. So we say that this transformation, this is a variational symmetry. This is a variational symmetry for J if and only if. So this is a necessary and sufficient condition, right, if and only if this following differential equation is satisfied. So zeta times del f, now well zeta times partial f partial x plus eta times partial f partial y plus eta prime minus y prime xi prime times partial f partial y prime plus xi prime f is equal to 0. So if and only if the moment we satisfy these this differential equation, we are guaranteed to say that xi comma eta is the infinitesimal generator or leading to our variational symmetries. Okay. The key thing is, let me call this as 1. the key thing is that this 1 does not necessarily holds only for extremals y, it will hold for all x and y in the given domain, which means we can, in order to find out xi comma eta from this equation, we can essentially equate the coefficients of various powers of let us say y prime, right, keeping x and y fixed. So, what I just said is the following. So, relation 1 holds for all y, not just for extremals, they hold for all y, not just for extremals, and we will see that. So, the other issue that I highlighted is typically xi is a function of x y and eta. So, xi and eta, they are both functions of x y, right. So, we can assume, since they are only functions of x and y, it implies we can treat our variable, we can treat y prime as our y prime, which is dy dx, as independent variable, right. So, they do not appear in the expression or in the expression for eta and xi, the infinitesimal generator. So, which means all we have to do is we have to equate to get eta and xi, we have to equate the coefficients of various powers of y prime. Okay. So, for example, let us look at a case as to what I just said. So, for example, suppose notice that I am going to use a shorthand notation. So, in particular, this expression on the right hand side is said to be a function w of x comma y prime. So, this is set equal to 0, right. So, in particular, suppose w is of this form, a y prime square plus b y prime plus c, set equal to 0. Now, typically a, b, c, they are all functions, right. So, they are all functions of x, y, eta, xi and eta prime, xi prime. So, these are all the variables that we can get, and similarly this is the same for b and same for c, right. So, which means all I just said is, to find out the relation eta and xi, we just equate these coefficients, which are coefficients of powers of y prime to 0, right. So, we get three relations here, 3 relations for two unknowns which are eta and xi, right. So, xi and eta, okay, right. So, which means it seems that the system is over determined, but we will see that is not the case, because xi and eta, they correspond to the infinitesimal generators of the variational symmetry. So, variational symmetries are very special, they will not be found for every functional. So, this, although it seems the system is over determined, we will see generally that will not be a problem. Okay. So, what I just said is that we can get over determined system, So, and that is not a problem, no problem, since variational symmetries are special relations, and not every functional will have them, has them. Okay. We will see these ideas through some examples very soon. Okay. So, the example that I have in today's lecture, so I am going to so this is a new sequence. So, I start with example number 1. So, the first example is, we recall our example in the previous lecture. So, recall example 5 in lecture 15, our previous lecture, and that for that we said we took a functional of the form x y prime square dx, right, and integral from x0 to x1. And so my condition 1 here, we directly use our condition 1. So condition 1 gives us the following equation. I see that this is, so I am just writing down. So the first term is xi y prime square. So notice that this is nothing but xi times partial f partial x, and plus there is no function of y, so plus a 0, plus the next relation is del f del y prime. So 2xy prime times eta x plus y prime eta y minus y prime times zeta x plus y prime zeta y. And so this is the relation del partial f partial y prime eta prime minus y prime xi prime, right. Okay. So then the other terms in this expression involves plus. So let me write down x y prime times zeta x plus y prime zeta y, right, and these are all set equal to 0. Notice that well, this last expression comes from the last term xi, so xi prime f in our condition 1. Okay. So let us now, so all that remains in this expression is now we have to equate the different powers of y prime. Okay. So when we do that, we are going to get, so comparing the coefficients of y prime cube, we compare the coefficients of y prime square and y prime, and so that's it. So we get the following expressions. We set all of them equal to 0. The first expression gives us x zeta y is equal to 0, xi y. The second gives us xi plus 2x eta y minus x xi x is equal to 0, and the third expression gives us x eta y is equal to 0, right. I call these relations as A, B and C. Okay. So from A I am going to get that xi is a function of x purely, right, because x cannot be 0 in general, it has to be xi y which is 0. And from C I get that eta must be equal to eta of well, do we have, well, this last expression is x times eta x. So eta here must be a function of y, right. Now we plug all this result into our expression for y square, right, y prime square, and what we get is, when we do that, I get, so xi of x plus, well, let me club all the x terms together, x times xi of derivative of xi divided by 2x plus eta, well, let me take 2 here, plus 2 times eta y is equal to 0. Now which means that this quantity that I am denoting with a bracket can be equated to the negative of 2 eta y, because now since notice that this bracketed quantity is purely a function of x and this quantity is purely a function of y, and then they are negative equal to each other provided both of them are constants, right. So which means what we are getting is that so we are going to set, so this means that xi minus x xi x by x is equal to a constant c 1 is equal to negative 2 eta y, right. So, that is what we will well, in fact, it is better that we put 2 here. So, let me plug in the 2 here and then it will be easier. Okay. So, this becomes negative eta y. So, I see that from here I get eta is equal to negative C1 y plus C2. So, that is my functional dependence on of y on eta, functional dependence of y on eta, and also solving the first equation. So, I have that xi minus x xi x is equal to 2 x C1, and from here if I divide throughout by x, well, what I have is, so eta y is, so I get, yeah. So, continuing, well, all I have to do is we have to solve for xi. Let me write down the solution. We have to just integrate once, and the solution that I get from here is xi of x is negative 2 C1 x log x plus C3 x. Okay. So, now notice, well, I must say that we have now got the infinitesimal generators, but notice that these generators are unique up to a family of constants, right. So, that is something I wanted to mention. I should have mentioned a little bit earlier. So, let us go back. My infinitesimal generators, my xi and eta are determined uniquely up to a constants, up to integration constants. They are determined uniquely up to integration constants. And so, let us come back to the example we are discussing. So, note that suppose we take my C1 to be minus 1, C2 to be 0 and C3 to be 0, right. So, suppose we take all these values, I get my generators, xi to be equal to 2 x log x, right, and my eta to be y. Okay. And this is the same result that we saw in our previous lecture, same result as in example 5, lecture 5. Okay. We saw that this was one of the infinitesimal generators, and we have recovered that through specific set of these constants. Okay. So, our next example shows that this whole idea of finding infinitesimal generators by solving this condition 1 may not yield any result. So, let us look at the case. The second example involves this functional, which is integral x0 to x1 x square y prime square plus y to the power 4 dx. So, we need to find the variational symmetries. So, find the variational symmetries. Okay. So, condition 1, using condition 1. So, I am not going to write down condition 1, but right away write down the coefficients of various powers of y prime, and so these are the 4 conditions. We get x square zeta y is equal to 0. Students should check that indeed we get all these conditions by equating the coefficients equal to 0, the coefficients of the independent variable y prime. So, I get x square zeta y, let me call this as condition A. I call the second condition 2 x xi plus 2 x square eta y minus x square psi x, which is equal to 0, right. And I also, let us look at this 2 x square eta x plus y for eta y is equal to 0. So, I call this as condition C, and finally, I have 4 eta y cube plus xi x y to the power 4, set it equal to 0. I call this condition number D, right. Okay. So, from here I can again immediately conclude from first relation that xi is a function of x, right, and well, there is one more. So, xi is a function of x. From condition number C, we see that xi y. So, since xi y is 0, I see that eta x must be 0. So, from here this condition I can see that eta x must be equal to 0 or eta is a function of y, right, because this quantity is 0 concluded from condition A. So, then we can use condition B and D. So, which means let us use condition B. So, from condition B, notice that psi is a function of x. So, I get 2x psi of x plus minus x square psi of x divided by 2x square plus eta y is equal to 0. And again I see that this is a function purely of x and this is equated to negative of eta y, and that is only possible, this is only a function of y, and this is only possible when eta y is a constant. Well, eta y is a constant, eta y is a constant, right. So, eta y is a constant, or my eta is a straight line. Let us call this as constant C3 y plus C4. Now, so we have found one variational symmetry. Let us now plug it back. Let me call this. So, from the last expression that I have from D, what I get is well, so D was the following. So, from D I get 4 times C3y plus C4. So, this is my eta y cube plus xi x. So, what is xi x? We haven't found, divided by y to the power 4 plus xi x. This is equal to 0. Notice that now again we have a purely a function of y on the left hand side. This is equated to xi x. So, from here, well, so xi is, so this is a function of x, right, and this is equated to negative of a function of y. So, from here I get xi x is again a constant, and which means, so this is another constant, which means I can find that my xi is a straight line. So, C1 x plus C2. So, I have found my variational symmetry in terms of family of 4 constants, but let us see what happens. So, let me call these two relations as my relations E. So, if I plug relation E into B, plugging this back into B, so use E into B. So, using E into B, I see the following. I see that this is 2x C1 x plus C2 plus 2x square C3 minus x square C1, and from here I am going to equating the various powers of x, I am going to see that we get two relations, C2 is equal to 0 and I get that 2 C3 plus C1 is equal to 0, right. And then we again use E into the relation D. Into D, I get that the following. So, 4 times C3y plus C4 y cube plus C1 y to the power 4 set equal to 0. I get the relation C1 is 0. Well, so C4 is 0, and I also get that 4 C3 plus C1 is 0. So if I were to equate all these 4 equations which is circled, I am going to get only one unique solution, C1 equal to C2 equal to C3 equal to C4 is equal to 0, or in other words I get that my infinitesimal generators xi comma eta, they are identically 0, right, or which means the conclusion is that there is no non-trivial, or in fact there is no variational symmetry in this example. So variational symmetries may not exist. Okay. So if they exist, they will satisfy, if and only if they satisfy the conditions that I have shown. So variational symmetries may not exist for a functional. It all depends if it is variationally invariant or not, the functional itself. Okay. So I am going to end the discussion on finding variational symmetries by extending the result of condition 1 to functions of several dependent variables, and then look at an example. Okay. So then let me state another result in the form of a theorem. So this is for several dependent variables, I see that, let us consider j of q bar equals integral from t0 to t1 L of t comma q bar dot dt, right, where q bar is q1, q2, qn, and my and let me consider my variational symmetry as the infinitesimal generator as follows. So is xi comma eta 1 to eta n. So these are my infinitesimal generators, if and only if a certain condition holds. So before that, let me introduce a function. So let me introduce the function known as the prolongation operator, the first order prolongation operator of this Lagrangian, okay, also known as PR superscript 1 of V of L, right. So V of L, this is nothing but xi del L del T. Students should not be very much confused with this expression, because they can right away look at condition 1. So this prolongation operator in this condition 1 will correspond to this, the multivariate version of this this underlined quantity, all these 3 quantities. Okay. So note that, so the operator becomes as follows. So this is plus, so we are working in several dependent variables k from 1 to n times, well, of eta k del L del q k plus p k of eta k dot minus xi dot q k dot, right. Okay. So where the quantities p k is del L del q k dot, and my quantity zeta dot is introduced here. The quantity zeta dot is del xi dot is del xi del t plus summation of q j dot del xi del q j, right. So this is xi dot is del xi del t plus q j dot del xi del q j. Okay. And then I have also eta k dot. So eta k dot is described as, so eta k dot is del eta k del t, essentially it is the chain rule, right, times summation q j dot del eta k del del q j. Okay. So essentially this is all the chain rule that we are applying. Okay. So then the result says then the transformation t, which is given by theta of t comma q bar comma epsilon, and theta and qk, which is psi k of t comma q bar comma epsilon, from is a variational symmetry if and only if I have the prolongation operator PR1 of VL plus L of psi dot is equal to 0. The prolongation operator plus this quantity is equal to 0. This is the multivariable version of condition 1. Okay. So, this is for all q, the extremal q smooth, which is a smooth function on the interval t0 to t1. Okay. So, let us look at an application of this result